My name is Derica Peters. I'm with the North Central Texas Council of Governments, and I am very happy to be here today and have you all here today with HAF and Associates hosting and training the event. So we have Ben Pilot with HAF, Scott Rushing with HAF, and Stephen Crawford with HAF here today, as well as Michael Wilkins with Urban Eco Plan. So with that, I'll pass it over to Ben.
All right. Thank you, Derica. I'm very excited to be here having this presentation, and thank you all for being here as well. We're calling it the NCTCOG iSWM workshop. It's focused on integrated design criteria and then kind of getting into some of the rules of thumb or lessons learned, if you will. And I'm excited to see several faces here that we learn these lessons together or from you or however else you want to put it. I think there's a lot of things that we've learned over the last 10 years. So we're going to be focusing on the iSWM manual from the COG perspective. And so we understand that a lot of communities have their own specific criteria. They've developed what works best for them. For the purposes of this presentation, we're really going to focus on the broader concepts. We're not getting into any specific criteria that would necessarily, not trying to contradict or get into the specifics of what each city does. So we're going to try and focus on high-level concepts, and like Derica said, we would love it if you guys would chime in with your experiences. That's really what we're here for, is to, there's not anything new necessarily for a lot of you guys. There's going to be things that you've been seeing and been applying for 10 years. But what we do think will be new and valuable as part of this is to share your experiences, share your lessons learned, to share your questions, the points of confusion that continually trip people up, or the things that could be clarified better. So that's really what we're out to get out of everyone. So we kind of have a panel, if you will, up here. So I feel like I'm echoing a lot. Does it sound funny? Okay. Sounds good to you, then that was good. So we have kind of a panel. I mean, we have a lot of different experiences from across the Metroplex, across the NCTCOG region. So really, we have folks that are working on the east side, the west side, and everywhere in between, working with counties, working with cities. So we're hoping that as we have that discussion, I don't think I can answer all your questions, but I hope that somebody up here can, or somebody in the audience can. So I think Ramin brings a few years to the table here that he could probably chime in on a few things. You know, Stephen and several other you guys here are doing a lot of this. So with that, we're going to go ahead and get going. We kind of had the welcome and introductions. I'll just ask, how many folks here work for a community right now, work for a city or a municipality? All right. And then the other side, we have consultants. All right. So how many of you have either adopted iSWM or work with communities that have adopted iSWM or applying iSWM principles? Is that okay? Good deal. All right. So what we're going to do, hopefully y'all saw the agenda here. We're going to go through really section 3 of the iSWM criteria manual. And so we have printouts back there. Hopefully you guys were able to get one and you can follow along with what the specific criteria is. And we're going to go through that fairly quickly. Like Derica said, we've got 2 hours, and we really want to get to those conversations and lessons learned. So this is what we're going to cover. We're going to start out with that overview of what is iSWM. What is the Integrated Stormwater Management Program? This is just a look at the region that the COG covers, the North Central Texas Council of Governments covers. Sorry, this is a little bit of an outdated figure, but generally you can see pretty well what the counties are and what the areas are that the NCTCOG covers. So what was the intention of it? Why did it begin? Well, it was really a regional program to assist local governments. That was really what NCTCOG is all about. That's what the iSWM program is about, helping to manage the stormwater program and also the MS4 impacts. That was a big program in the last 10 years, and hopefully the iSWM program has helped to smooth that out, to help meet those requirements. It's a collaborative effort, over 60 local governments. There's an iSWM subcommittee, which some of you participate in, that helps guide the program, which is a subcommittee of the Regional Public Works Council. So I'm kind of giving a little background here. Right now, HAF is leading the team along with Urban Eco Plan, and Tetra Tech as a consultant to the iSWM program. So just trying to set some of the background here of what is the iSWM program. So traditionally, there's been a lot of discussion about stormwater impacts and stormwater rulemaking and what are the future regulatory requirements that could come up impacting stormwater. So I brought this up to give a history. I think right now there's not necessarily anything that's really clear that I'm aware of as far as where the nation is going with stormwater rulemaking. But historically, it has been something that's been talked about quite a bit, whether there will be more stringent stormwater water quality requirements. Maybe there's going to be enforcement through the MS4 program. There's a lot of discussions that have gone on. And so I thought this map was just relevant to show people across the country that have adopted either some version of water quality and or retention policy. Obviously, in North Texas, we have our own unique applications and requirements. I mean, we have our own specific restrictions, I would say, with our soils. It's very difficult to retain. It's very difficult to infiltrate. So we have our own challenges, but the point is that a lot of people are transitioning that direction. A lot of the drivers for these communities were combined sewer overflows or EPA requirements. So everybody has their own challenges, but I just thought it was relevant in terms of, you know, the conversation that's occurring and why you would want to look at something like iSWM for a regional program. It's because a lot of folks are starting to trend that direction. So why iSWM? Well, we understand that increased runoff leads to flooding. We know that there's impacts that result from that. We can't just pretend it doesn't happen. It does. We know it's streambank erosion. It's a very big issue for a lot of the communities in North Texas. The water quality concerns, stormwater regulations, we have these loss of natural features. So we continue to see development, reclaim, take away and lose those natural features that we'd all like to maintain. So what iSWM provides is a more comprehensive approach, looking at it in an integrated way. I mean, we're going to use that word a lot, but it really is true. Trying to look at both water quality, streambank erosion, and flooding all as one. And I think the regional consistency is a big part of it. I think originally the goals were trying to establish the baseline of what communities would look at and to try and give some things to consider, to try and provide some technical resources that communities could rely upon as we look at trying to develop some consistency. We all understand the age-old adage that the watersheds don't recognize community boundaries, right? That we can't just, you know, put up walls and do our own regulations and expect that we're not going to be impacted by each other. So we are all connected across community boundaries. So some of the basics of iSWM, and again, this is going back, is to address stormwater earlier in the development process. And so we gave this presentation internally actually just kind of as a vetting process for some of our engineers at HAF. And, you know, a lot of them were very young engineers, and to them it was just kind of always a given that, yeah, stormwater is something that we're going to look at early in the process. Now, it hasn't always been the case. You know, 10 plus years ago, you know, a lot of times we were being handed site plans and saying, go make it work, you know, and that's trying to get away from that, trying to educate and get people to consider stormwater earlier in the process. The concept of multiple storm events, that's also something that I think we do very often in a lot of communities, something that wasn't always done, and we'll talk about why it's important. Integrated site design practices. So again, used to not take into account the topographic features where you had natural areas where you would try and preserve. And I think iSWM tries to highlight that and bring it up. And ultimately, we're trying to reduce the impacts, whether that's water quality, streambank erosion, or flooding. So that, I think most people would say that the downstream assessments and the things that we're looking at off-site in terms of impacts has been one of the really monumental or kind of transitional type of concepts that's been incorporated. So, and then protecting water quality during construction. Lee does a great training on that just about, I think it's about every year. It seems like, I don't know if it's every other year or what, but does a really good training on construction activities and water quality. So Derica alluded to some of this. There is great resources, I will tell you, available through the COG. First of all, you have the criteria manual. That's the top left. So this is through the website that Derica mentioned earlier. If you search NCTCOG criteria manual, you're going to be there. The criteria manual, you have excerpts of right there. Communities will take that. They'll customize it to their needs, their requirements. The technical manual, this is the more scientific. It doesn't change a whole lot. How do you calculate capacity for an inlet? It doesn't change day to day. It's pretty much the same. So these are the equations and methods. It's a more technical reference manual. It's exactly what it is, and it's a very good one. So people use it across the state. I will tell you, we have experience with a lot of folks outside the region that'll just want to see how somebody else is doing something. They'll pull this up, and it's a great resource. Tools and training, there's a lot of archived seminars that people have given over the years, whether that's bioretention or whether it's downstream assessment. There's an entire presentation just on that. There's great tools and training, and then program guidance with supplemental guidance documents in terms of how do you apply the iSWM manual. So with that, this is what Derica mentioned earlier, some of the iSWM communities. So you can show the timeline of when different folks have adopted iSWM. Going back to 2006, you see Fort Worth and Grand Prairie were in 2006, and you see a lot of other communities have joined since then. In 2014, there was a shift from adopting iSWM to more of a points-based metric or an outcome-focused implementation. So with that, and I think this is on the sheet that Derica has at the back of the room, It shows a lot of the communities that have adopted iSWM and have been certified. So several of the ones up here on the screen were certified. And so that's really the focus of where iSWM is headed now, is this outcome-based implementation. So you may not want to adopt the entire iSWM manual, but maybe you have your own downstream assessment. So you're looking downstream, so that would be something you would be given credit for. There's a number of different metrics like that. For communities that are looking to become iSWM certified, at the end of this work effort, we expect that there will be some ordinance language that's out there for people to adopt to implement different iSWM measures. So with that, I'm going to go ahead and turn it over to Scott. He's going to go through the hydrologic methods.
All right, thanks, Ben. So as Ben mentioned earlier, try to keep it kind of high level, more just concept driven on some of these sections that we're going to go through. I know in some of my slides I do have some numbers that are relative just to the COG manual specifically, but each community has different numbers and different criteria, technical criteria. Anyway, try to keep it high level today, so we'll just jump right into hydrologic methods. So this is table 3.1 from the COG manual. So this is applicability of hydrologic methods. So on the top row there, you can see that, we'll just kind of echo you up here. You can see the different methods up here. So you have rational method, SCS, Snyder's, both kind of unit hydrograph methods, and then modified rational, USGS text equations, and iSWM water quality volume calculation. And then obviously over here you can see the different applications. So rational method, obviously going to be more towards gutters, inlets, storm drain pipes, smaller sites. SCS method and Snyder's method, both unit hydrograph, really applicable for a wide range of activities. And modified rational with storage facilities, and we'll kind of get more into that in a little bit. Okay, so constraints on using these hydrologic methods. Most of these are size limitations, but some of them are what level you're at in design. Are you at a concept level, preliminary, are you at final design? Rational method typically would be for like smaller sites or storm drain design for a subdivision. Modified rational, there's a lot to cover there. So with modified rational, typically most communities, what I've seen is at a concept level, they're okay with modified rational, but then when you get to final design, usually you would go towards more of a unit hydrograph-based method. I know some communities will allow modified rational up to a certain threshold. So modified rational is one of the ones where you definitely want to be aware of which community you're working in as far as what the limitations are. Obviously, SCS and Snyder's are great for basins or a watershed if you're looking at a creek. Textile regional regression, more of a rural application. Obviously, that's going to be used in like a larger watershed, like 10 to 100 square miles. You're not going to use that on a small site. And USGS regression equations, those are allowed as well. However, a lot of times, I think most communities use that as kind of a comparison point, not necessarily something you would use for a final design. Okay, so we're going to go through some lessons learned, as Ben mentioned from the beginning. So, based on feedback, preparing iSWM submittals and assisting in drainage reviews throughout the COG region where iSWM criteria have been adopted or iSWM design principles are being applied. So we'll go through a few of these for each of these sections. Okay, so first with hydrologic methods, one of the big things we see is off-site drainage areas that aren't shown or aren't taken into account. So you can see the site here. You can see the big red outer boundary with all the colors in the middle. So this is your site. This is your drainage area map for your site. But what's not shown on here is your actual off-site drainage areas. So you can see these big blue arrows up here to the top of the screen. Now, if you were to just take one of those basins from your site and calculate how much you've increased going to the north, you may find out, oh, it's not that much, and maybe I'm fine downstream. It's not too big a deal. Now you actually bring in that off-site area and combine that in with whatever you're increasing from your site. Well, now you may actually have so much water going north that the increase that you have now may actually be an issue. So you really need to take into account off-site drainage areas. I think this next exhibit kind of show you more bigger picture. So this blue site would be what we were showing at that red boundary, just your proposed site. So then you have this large off-site area here off to your left. And so when you combine that in, coming up here to the north to discharge point A, and take that into account with your local flow that you're increasing, well, now you have a totally different analysis now, leaving point A when you start looking at a downstream assessment. As far as point B over here, you actually have a large offsite area contributing to an underground storm drain system, in this site in particular, tied into that system. So you're going to need to be aware of all these offsite drainage areas draining to features that you're going to contribute to. And I'd say not just the offsite areas that are going to contribute to existing systems, but maybe offsite areas that actually flowed through your site that you're going to have to convey. So we put in this slide. This is a useful tool. This is Dfw Maps.com, and you can pull this up and you can locate where your site is, and you can turn on the actual HUC watersheds. And so this is a good thing to do, a good exercise to run through, maybe beginning on in a project when you're putting together an iSWM submittal. Kind of helps you get a perspective on where you're at in the watershed. You know, are you in the upper end of the watershed? Are you in the lower end of the watershed? Kind of middle? Is there a major highway nearby? Is there a creek nearby that you plan on discharging to? Is there an old neighborhood just downstream that may be undersized? I think it's just kind of a good idea maybe to use this as a tool, just kind of for planning purposes. Okay, and another lesson learned I want to share was impervious areas. So if you take a site and let's say you're going to just a blanket apply a C factor of 0.8, now you could do that, but you may have multiple discharge points from your site. So if you were to actually go through and break up your percent impervious based off of your actual impervious area, then you would find you'd get a much different C factor for each basin that's going to these different outfall points. So you may get 0.84 for this large area, and you're sitting at 0.9 for just this little basin that's along the roadway. And then for this area here that's a part of your plat, but not actually going to be developed, it's an open space area. It's got 0.3. So this could really hurt you or help you. So if you're going to, let's say if you applied 0.8 to this area that's actually 0.3, you may end up having to run some analysis on this pipe that you didn't really have to do. You may potential there for saving your clients some money. But then also, you maybe say, hey, it's at 0.8, but in reality, it's primarily all paved. You may be closer to 0.9. So you just need to be aware of knowing your discharge points from your site, how many they are, where they're located, and looking at these impervious areas on a more micro level and seeing, how may this impact my different outfall points from my site if I was to actually calculate a weighted C for these basins. Go ahead. Yeah, sure.
What do y'all think about that? I mean, a lot of times we have paved area, we have building square footage. It seems like that's something that's pretty straightforward as far as something to calculate. But we see a lot of people trying to use land use. I think that's maybe a carryover from back before we really had the detailed aerials that we have now and the things like that we can use to develop those impervious percentages. But a lot of times it does make a pretty big difference, I'd say, on the site. So is anybody else seeing that? Does it seem to be an issue? Not really?
Okay. Well, I know Ben mentioned at the end of each of these little sections we have a chance for some Q&A. I would appreciate your feedback. This is a chance to open up discussion to you guys. Y'all have any questions or any thoughts, in particular hydrologic methods?
In one of your earlier slides, you have a note about pending NRCS modifications.
Yeah.
The methodology.
Yeah, Ben, you want to answer that?
Yeah. I don't know if you've seen it, and I haven't dug into it enough. So here, let me swap with you there, Scott. Michael, you've got a mic here as well, so you chime in if you've read into it more. But it's my understanding, basically just a coalition of different folks that are looking at that type of thing. People that were fairly into the equations and the rationale and the justification for how those different equations are developed. They went and looked at it, and they had some concerns about the way it's being applied now. And obviously, the SCS method was originally meant for soil conservation and things like that. It's my understanding, just reading through some of the notes, and it's available online. If anybody's interested, you can email me afterwards. I'll send you the notes. And Michael actually pulled it out originally. They were concerned about some of the more extreme events that come through, the really flashy, the hard-hitting storms, and whether the SCS method's actually accounting for that correctly. Also, some of the variability, I would say, of the curve numbers across the state, and then the antecedent moisture conditions. So I didn't read anything that drew conclusions as to how they would address that, but it was more bringing up concerns and potential for changes. Now, Mike, will you tell me if I missed anything in there?
No, I think you've covered it all. A lot of the challenges related to those flashy, frequent events, the really intense storms, it's created challenges with the design of BMPs that are really meant for smaller volume events, for when you're talking about water quality volume. And there's been a lot of overlap, so it causes some conflicts on how you design structures that are meant for conveying something like a 50-year event or a 100-year event, the longer duration, high volume events. And I think the modifications to it, they're looking to address the water quality design, so there's not as much conflict, and in many cases, over-design.
Yeah. So obviously that could have big impacts, right? I mean, we use SES an awful lot in this area, so it's something to watch, something to be aware of, and something to kind of challenge us as well. I mean, just because we've been doing something the same way for forever and that's the way it's been done, it doesn't mean that people aren't still looking at ways to improve it. So,
and it's easy to manipulate too. If you make just a minor adjustment to just a sheet flow number or time of concentration, consequently, that's a huge change in volume that you're designing for.
Right.
And designers can take advantage of that if you're really trying to fit a dry detention basin on a small site. Tweak one of those numbers, you can fit that in. So the idea is to try and pull the reins in on that.
No, go ahead.
You're still seeing people use the 300-foot sheet flow value rather than the 100-foot value that was advised to make 10 years ago?
I think we do see it every now and then. People try and use it because they weren't aware of the updates or something like that. So, Scott, you probably look at more of those than I do.
Yeah.
I think it depends on the community too. Some communities haven't made those updates. If they haven't, then you're typically going to see a designer use that 300 feet just because it'll typically will fit more lots in or fit more impervious surface in.
Yeah, I don't know if I have much more to add than that, but yeah, I do see that. It still occurs, but yeah, we usually comment on something like that. All right, any other questions? Comments?
Talk maybe about Atlas 14, tracking that, you want to talk about it?
Yeah, so with Atlas 14, I don't know if y'all been following the updates there. It's primarily going to affect more the central Texas and more coastal regions. Up here in North Texas, you're actually not going to see a whole lot of difference with Atlas 14. The numbers are pretty similar to what they were before.
Are you all aware of that? It's changed the majority of the rainfall data we've used. It hadn't been updated in 50 years. So.
Right. Yeah, so you won't see much change in that Atlas 14 update in this region.
Any other questions?
Nope.
All right. I'm going to stand up really quick and say hello, and I'm just going to hang out here since I've written down some notes that I want to refer to as we talk about the water quality component. Before we get started on that, I'd kind of like to get a feel for what your experiences is in terms of working with the water quality design guidelines through iSWM. Has anyone submitted a project, designed a project, or reviewed a project that's been submitted either by the first option, which is integrated site design, the second option is treating the water quality volume, and the third option is off-site treatment? Does anyone have any experience with those types of designs or submittals?
Reviews, right?
Mm-hmm.
A little bit with the second option.
With the second option with the water quality. And that makes sense because the majority of the communities that have adopted iSWM that do have the water quality component, it's either a voluntary design practice or some of the other communities have adopted the practice where you have to manage the water quality volume specifically. So we haven't seen a lot of sites that have utilized options 1 and options 2. And what we want to talk about today is the experiences we have had with those sites that have submitted those designs with options 1 and option 2, and things that we've seen, and some actual synergies between those three. There's an awful lot to talk about, and we won't be able to cover it all today, but I want to point out some of those lessons learned and pitfalls that are actually kind of similar to planning and design, where you may change a sheet flow number and start adjusting volumes and things to fit designs in. But we want to point out there are a lot of resources out there, and there are a lot of compelling reasons to start utilizing these other options, because that actually leads to higher value developments when you can fit that in. And when you're talking about the regional application of it, understanding the broader need for implementing water quality controls, understanding where your site is located within a specific watershed, because we're getting to the point that we have just many watersheds, many of our creek systems that are impaired by either bacteria levels or other pollutants such as nitrogen and phosphorus. So we're going to see these types of designs become much more relevant in the coming years, and I don't think it's all going to be driven by regulation. I think it's going to be it's going to be compelled by a desire for higher quality designs, and we're seeing that with communities that are competing with each other to attract new developments, and this desire to have more green spaces and more quality natural areas. So I'll get off my soapbox there and start moving through the lessons learned. I could probably talk about water quality all day, and I know no one wants to do that on a Friday afternoon. So I mentioned there are three options. You have the integrated site design, which is a points-based system. We're not going to go through all the ins and outs of those, but it's included in the criteria manual. I encourage you to kind of read through that and look at it. And, as you do that, if you start having some thoughts and questions, what would make it easier for you as a reviewer or a designer to integrate this type of design development review into your processes? What can we do with iSWM to make it more palatable to the design community, more palatable and easy to track for your communities? That's what we want to hear. That's the feedback we're looking for over the next few years as we work to modify iSWM and add to its usability. The integrated site design, as I said, it's a point-based system. It's based on really 4 practice areas. It tries to encourage the conservation of natural features and resources. It tries to encourage the use of low-impact design practices. It encourages the reduction of impervious cover and the utilization of natural features. And the utilization of natural features is really saying, hey, take a look at your site. What are some of the natural features that exist beyond just the floodplain? Where are the natural features such as natural swells, natural riparian areas, et cetera, that exist that you could utilize as part of your open space requirements, but also as your stormwater management requirements, and also, even just as important, amenities for your site. So you can start looking at how would that work where you're trying to integrate hike and bike trails for a larger site, connectivity to the regional trail plan, et cetera, and going beyond just putting your floodplain boundaries on a site plan and then going from there to create your site. And what's great about this is that there are so many resources available that go beyond looking at floodplain. There are GIS resources available from Texas Park and Wildlife, from TNRIS, that you can quickly overlay onto a site before you even start the site plan process, so you can identify these natural features that can be integrated into these designs and actually make it much simpler to add these points to your iSWM application if you go that route. So, there we go. And the second one, this is the one that we see most frequently, and that's the treat the water quality volume, the 85th percentile rainfall event. I know there's been some discussion about is the 1.5-inch rainfall too much, too little? Ben, did you want to add anything to that discussion? I don't know if there's been any changes recently.
No, I don't think anything's been changed from that.
So as it stands now, we're looking at the 1.5-inch rainfall. But in all honesty, depending on the site, whatever volume that you can feasibly treat is beneficial. So if you can't quite get to that 1.5-inch volume, treating 1-inch volume for the site is going to be beneficial in the grand scheme of things. This is helping us really start to address total suspended solids, and one really big issue that we're going to see, that we see now and we're going to see in the near future, is how do we start managing floatables, trash, and debris, and that's going to be part of this water quality volume treatment as well. Regional approach. This is one of my favorite options, and it's one of the more difficult ones, because if you look at the grand scheme of things, and the image I have here is the Rowlett Creek, West Rowlett Creek watershed. I'm sorry, the entire Rowlett Creek watershed. And within that, I've got it subdivided into all the smaller sub-basins. And inside that entire boundary, there are more than 10 individual municipalities. So if in the grand scheme of things, we're trying to improve the water quality in Rowlett Creek, which coincidentally is our latest creek system to be added to the 303D list, which means it's impaired. It's impaired by elevated levels of bacteria, so it technically doesn't meet standards for recreational use now, which is the same impairment that the Trinity River has. Some other issues that we have with Rowlett Creek are debris, trash, and floatables. And it's going to be important to address that because that obviously is one of the major contributors to one of our largest water sources in the Metroplex, Lake Ray Hubbard. So we have all these communities involved. We have Dallas Water Utilities, who manages the reservoir. Those are a lot of constituents that have to be on board for a regional approach to actually improve the water quality in that watershed. So again, that's one of the important things to keep in mind. Where is your site located? What are the opportunities to collaborate with other communities to start inching towards that regional approach? And it can be a single site. When we're talking about larger developments in, let's say, Frisco, the understanding that that development is impacting Rowlett Creek downstream, theoretically, if there's not enough room on that site to treat the water quality volume, potentially there's a park downstream in the city of Plano that could help achieve that volume. So that's what starts those discussions between the communities, and it starts with that single development and the impacts it might have. So the lessons learned, I'll stop right there and see if anyone has any comments related to regional water quality in general, any challenges that you face as a designer, challenges you face as a reviewer at a city.
I have a question. So I'm actually from Washington State, and so designing their water quality was built into our design. So, you know, making sure we were accounting for that stuff was a part of our design. But when I came down here, I noticed it was not. And so is it community driven, or is it driven by the client? Because it does create increased cost to the client, right? To do water quality is going to be more financial cost to them, right? When we start, as a designer, as an engineer, if I start incorporating those types of things into my design, it's a cost to them, right?
Yeah, and it depends on the site. A lot of times you'll see, if it's a site that's very constrained, when you start adding in more landscape features, more water quality features that take up space, it depends on how it's planned and designed. If you can integrate it into, let's say, your landscape requirements, if there are open space requirements and you can integrate BMPs for water quality into the open space requirements, there are ways to make it work. But a lot of times there are conflicts between landscaping requirements, setbacks, parking requirements that you have to work through. So it goes both ways. Sometimes it may add some initial costs, which is difficult to work with through a developer because they're generally interested in those front-end costs. But again, it really starts at the planning phase. And what we're trying to get at here with an integrated approach is if you identify those natural features that could function to provide those stormwater management features, let's say you identify a large somewhat natural swell on a site. And I'll give you an example here. We're looking at, it's about 800 acres in Frisco right now, where it's outside of a floodplain boundary, so when you look at it and you're just looking at topo, you're not going to see a floodplain. But as you dig in and you look at resources that identify natural features such as riparian areas that have been mapped by Texas Park and Wildlife, and just looking at the topo, you can identify natural drainage features outside of the floodplain that could be integrated into a site. So it facilitates the design of the site by utilizing a natural volume that already exists. And then if you're looking at how do you integrate that into the overall site design, perhaps that's your open space that the development focuses on, and also provide you that volume. So the idea is that the earlier in the process you start looking at where can these BMPs be located and function the best, you're going to have a better opportunity to reduce the cost to put those in, and ideally create a much more natural site, much more aesthetically pleasing site, and a higher value site.
But, and you all said, so I mean, iSWM, for cities, so a lot of the work that I've done is in the city of Fort Worth, and so they require you to submit iSWM. But then you're saying the water quality part is optional. So why wouldn't they just require you to do it, the water quality?
You want to take that, Ben?
Can't speak for the city. I definitely can't do that. But I mean, yeah. I mean, I don't really think there's anything we can say as far as from the city's perspective. I mean, it's out there. I mean, people are considering it. Some people are encouraging it. Some people have it as an optional area. But you know, I think each community is different why they have or have not. So I really can't speak for them.
But as an engineer, when we take it upon ourselves to develop a site and implement those types of things, then the city will see that it's a beneficial thing or something and start incorporating it.
I think any city would be happy to see a submittal that says we want to incorporate all these green infrastructure water quality features, because that's one. It's creating a site that's not going to contribute further to the degradation of the receiving stream. It's helping them meet their MS4 requirements. So it's not something that, just because the city doesn't require it, doesn't mean that's something that they would not entertain.
I'm just blown away by it. Since I've been down here, I'm just wow, I know how to do that.
And well, it's different, and I'll give you my perspective. I'm from North Carolina originally, and there we had very visible evidence of the damage that stormwater pollution could cause. We had fish kills, et cetera, so there was a direct impact on the fishing industry, and it was something that was covered in the media, just easy to see. And so just like I think Washington State, too, with the salmon industry and other impacts related to water quality degradation, there was a big driver there. Just geographically and where we are in North Texas, there aren't really that many visible indicators, but what is moving the needle now is recreational use. And I think Fort Worth is a good example. The Trinity River in Fort Worth meets the standards for recreational use upstream of downtown. And a lot of their economic development is centered around the Trinity River with Panther Island and all of that. So they are very inclined to maintain that water quality. And so there's going to be a bigger emphasis on integrating those features into site designs. As you move downstream and you get to Dallas, where the Trinity River doesn't meet the standards, and there is that stigma that the Trinity water is actually it's not looked at as a clean water resource, and it's hidden by levees. It's not as visible. So there's a struggle there to be a community that has multiple communities that discharge into that system. It's more and more difficult the further downstream you get. But I think that's what's going to drive it. The Trinity River doesn't go into a reservoir until you get to Lake Livingston, and that's very far south. But the example of Rowlett Creek, which discharges into Lake Ray Hubbard, which is a Dallas Water Utilities reservoir, I think that's going to drive a lot of change in that basin.
One thing, Mike, I might bring up, and you probably touched on this, but I think in yours and my experience, both of the Carolinas, I mean, if
boils down to, there's one of two things that drives water quality, stormwater quality. It's either public demand, quality of life, or regulatory mandate. Which one comes first is where the point of contention comes in. As you pointed out, most cities don't want to jump in and be volunteers to go out to the spear point and move forward until it's demanded either by their residents or it's mandated by the state or the federal government.
And that's a really good point, and it goes to your point as well. There's so many people from so many different areas of the country relocating here. I mean, the economy here is incredible. It's like nothing I've ever seen. They're coming from communities that, you know, let's say Chicago, where combined sewer overflows has required green infrastructure implementation. They're used to it. They've seen it. They're wondering, where is it here? So there's going to be more demand from the citizens, and that's going to bubble up through councils, et cetera, and I think that's going to start changing it. You'll see broader scale implementation. We've got a lot to cover, but this is going to be shared with you. I put some of my points, things that I've seen on plans submitted, where some pitfalls are. What are some ideas of how to avoid those pitfalls and start creating more, facilitate your integrated design approach, and I'm happy to discuss that with you further offline. If you have challenges with your designs or reviews, please do reach out to me.
Thank you for the question. I think that's a good conversation. The next section we're going to get to is acceptable downstream conditions. So we're going to attempt to cover a lot in a fairly short amount of time, so I'm going to really lean on you guys to bring up your questions and experiences. So, as I said before, I think that most people in the industry have acknowledged the downstream assessment as being one of the more impactful components of the iSWM manual, both in terms of refocusing, you know, where exactly you have to evaluate your impacts, and then also just being a kind of a paradigm shift in the way that we look at it. So we're going to go through a couple of examples here and talk a little bit about it. But I think first it's important to understand kind of the purpose of what the downstream assessment is, right? Because a lot of people would just say, oh, let's go build detention, and you're done. We don't have to worry about it, right? Some people have taken that approach. The downstream assessment is attempting to come at it from a little bit different perspective. So you're looking at it, and the focus is the same. We're all trying to protect downstream properties from flooding or velocity increases caused by upstream development, right? And I don't know who wrote this originally. It's been, the criteria manuals kind of get shared around, right? Somebody comes up with the concept and different people do it. So I don't know if we could track who originally came up with the concept of a downstream assessment or a no adverse impacts, but I have to think it was probably as a result of legal precedent, because I think that's where a lot of this comes back to, is you're trying to provide defensible evidence that a proposed development does not impact downstream assessments. So as engineers and as communities, we see a lot of liability associated with that. And what's the first thing that happens, right? We've all got an example. We could probably go down the row here of a development that goes in and somebody downstream floods a few years later, and what's the first thing they do? Is they go, well, I never flooded before. This property wasn't here before, so obviously I've correlated those two and said that I flood because of that person. And a lot of times if a community can't quickly bring out a piece of paper and say, well, we've proven that that's not the case because we reviewed this downstream assessment or this evaluation or this analysis to show that they were allowed to go in. If you can provide that document quickly, a lot of times you can avoid a lot of conversations about that fact. If it doesn't appear that very thorough analysis went into that, you can see that conversation kind of grow. You can see people start to get more concerned and more leery about it. So a defensible evidence, I think, is one of the more important things that you have coming out of a downstream assessment. Potentially eliminate the need for detaining increased runoff caused by development. So that's really the focus here of the downstream assessment, is if we were to look at it a little bit closer, and if we were to actually look downstream, it may be that we don't always need detention. There may be a pipe down there that was designed for the 100-year event that conveys that water to an adequate outfall and causes no issue. In those cases, why would we want to put in all of these small detention ponds everywhere that someone has to maintain, and it's not creating value, and it's not creating better quality of life for us? So the downstream assessment is intended for us to take a little bit bigger picture look at what's going on, and let's figure out what exactly is needed and why. So that's really the focus of it. So making better and informed decisions. I think looking at the overall picture, looking at what makes sense for everybody involved. So there's a lot of information on here. Like I said, we're going to go fairly quickly, but the technical guidance and training, again, Google is incredible, right? If you type NCTCOG and training, you're going to get that link and you're going to find videos for an hour-long training on just this topic. So we're going to go through it and pretty quickly get to some experiences, but if you want to know a very detailed approach on how to actually calculate it, there's a good video in there. The hydrology, so this is the technical manual, not necessarily the criteria manual that you all have. The criteria manual is going to tell you which storm event and when and where. The technical manual is going to have that more detailed equations. In section 2.0, you can find a very detailed description of how to perform a downstream assessment. So I'm going to refer you to those, and then we're going to kind of move quickly unless you guys have questions about it, and I'm happy to stop and answer any of them that you have. So here's the concept. So we're going to get into hydrographs, which always makes us, smile, right? We're civil engineers. Hydrographs make me happy. I don't know why, but let's go with that. So we've got two streams here, right? So we've got blue lines, right? Center lines. So we have, let's call this tributary 1, and this is being tributary 2, right? So we got a hydrograph. It's flow versus time, right? So we've got tributary 1 over here in the before development. So tributary 1 is the gray graph that you see there. And so that's the volume and timing of the runoff coming from tributary 1. And so let's assume that we have a time and that from when the rain starts that storm is going to hit 12 hours. And 12 hours from when it starts raining, you're going to see the peak of that storm event hit the confluence of that next stream. Well, the other watershed, tributary 2, is a much bigger watershed. It takes longer to get there. Maybe it doesn't get there until 16 hours, right? So we got a 12-hour and a 16-hour, so there's a little gap between the two. So what happens? You got a peak flow that happens as you combine those two hydrographs, and that peak flow impacts all that reach downstream of when those confluences come together. But if I put in a development off of tributary 1, and I decide I want to put in detention, I've now slowed down or attenuated that hydrograph. I probably have more volume. And so even though on my side I've lowered the peak discharges, as a whole I may have caused a negative impact downstream because now that peak of tributary 1 hydrograph is actually closer to the peak of tributary 2. And cumulatively, those two are having a bigger impact downstream than they would have if I wouldn't have done detention at all, right? So conceptually, does that make sense why we would look downstream? Makes sense why we would do a downstream assessment and not just always do detention, because this comes up a lot. People just say, oh, let's just detain everything. Well, if we slowed all of the water down, have we really done anything, or we've just moved everything back a little bit, right? So conceptually, it makes sense, right, why we would want to do this, why we'd want to look at that. So I think keep this in mind as we go forward, and we'll evaluate. The step-by-step process will show you exactly how to do this, right? So you would do your hydrology for all of your basin, and then you would do a pre- and a post-development hydrology for just your site. And you would change those two, and you would see what the impacts are at that confluence and downstream of that confluence. So that's the concept of a downstream assessment. So is there anybody who wants to add to that? I know there were several people in this room that were probably around back when the downstream assessment and was just first being introduced, and if anybody has anything you want to add on the history of kind of the downstream assessment and why it was intended for, feel free to jump in at any time. So the process. So when performing a downstream assessment for a site, it gets very similar to what Scott said earlier. The first thing you want to do is identify where are your outfalls from your site. A lot of times all of my site goes to one direction, but sometimes it splits in two. Half of my discharge goes this way, half of my discharge goes that way. In that case, I've got to evaluate both outfalls. There's no way around it. So if I'm chasing downstream impacts, I've got to chase it in everywhere that water is increased or leaves my site. So the data collection, it's getting better and better, right? We've got more resources. We've got GIS. A lot of people have georeference plan sets. I can get the data more easy than I could 10 years ago. I don't think there's any doubt about that. And having that data is going to make this an easier and more seamless process. So to determine the downstream limit, we're going to really touch on that on the next slide. We want to figure out how far do we have to go, right? That's the question a lot of people have tried to answer. How far do I have to go downstream? Because I may just go 1,000 feet, and then I may come in and talk to somebody, and they go, no, you got to go a lot farther than that. Well, now I got to go redo my analysis, right? So that's one of the real concepts of why you'd want to have these discussions early in the process. That's why there's a preliminary iSWM submittal that's suggested. So you can sit down with somebody and say, here's my site, here's about how big it is, here's my watershed. I think we ought to go down here to this sump inlet right there. I think we ought to go down to that bridge. Don't you agree? Based on the areas, I think that's a pretty good stopping point, right? You can have those conversations and agree on how far your analysis goes. I think that's a really good utilization of a preliminary meeting or a pre-submittal meeting. So you determine that downstream limit. We'll get into that. Perform the hydrologic analysis, and then analyze what those flood conditions would be as a result. So we're going to go into the downstream assessment methods. All right, so I'm going to hope that I get these right, because we're going to go through a couple of examples, or I want to get it thoroughly. I want to communicate it right. So the adequate outfall. It's any location that you've determined to be an acceptable outfall that does not create adverse flooding or erosion conditions downstream. All right, so that's a long version. So what does that mean? You might want to tell me what would you consider an adequate outfall? Would we consider a major river, okay, the Trinity River, right? It's huge. Would that be considered an adequate outfall? A lot of people would say yes. Some people might say no. It's kind of up for each community, I think, to determine what they consider an adequate outfall. But you can interpret that in a lot of ways. A lot of communities have plans, right? We've got as-built plans. I can tell you that along this road, we designed this pipe 2 years ago, and it was designed for this much Q. And are you bringing more stormwater? Are you bringing more drainage to it than that Q? The answer is no. A lot of communities will tell you, well, that pipe was designed adequately to convey your site. And we agree that's an adequate outfall. You can move forward. Some communities will say your runoff coefficient was less than that pipe was designed for. If you can prove that to me, we'll consider that pipe adequate. So there's different things that people consider adequate, but ultimately you're looking to determine a location that you don't need to analyze downstream. If I could get my water to there, I'm good, right? And this kind of goes to the basics of what we do, I think, in engineering a lot of times, is you're trying to answer that question even before we had defined what adequate outfall was. Even before there was an iSWM manual out there, people were trying to figure out what happens if I develop this site. Where do I take my water? How far do I got to go? All these things are conceptual things that we've been doing for a long time. I think iSWM brings it together into a more structured and process-oriented approach. So, zone of influence. So this is the question of how far downstream. So I couldn't find an adequate outfall. I don't have design plans. I don't have the Trinity River. I don't have any major water course. Maybe I'm in an urban area or developing smaller watershed. So I don't have an adequate outfall. I've got to decide how far downstream do I go. So this is where some rules of thumb come in. So we're going to go straight into the lessons learned as we look at a couple of examples here. And I'm going to go backwards, so hang with me here for a second. Oops. So I think we're going to start with, we'll start with this one. So the 10% rule was designed as a rule of thumb to tell people approximately how far you could go downstream. So 10% means when my watershed, the watershed that I'm impacting, is less than 10% of the total watershed, then I'm no longer having a major impact. So my runoff is such that it's not really having a significant or measurable impact on what's happening downstream. So in this case, we have a site right here, and that's the blow-up of the site. And let's say it's 10 acres. I'm going to make up some numbers here. Scott actually did this one, so he can tell you the real numbers. But let's say I'm 10 acres, and the rest of this is 90 acres. We know it's more than that, but it's simple math, right? So at that point, just downstream of my site is 100 acres. So the odds of my impacts to that watershed having any impact downstream at that point becomes statistically negligible by most studies. So they've done looked at a lot of different sites. People looked at master drainage plans and a lot of other data. And so statistically speaking, when you're 10% of the overall watershed, you're probably okay. You're probably not going to run into that situation with the hydrograph timing that we talked about earlier. So that's kind of a general rule when you want to figure out how far downstream. Please don't take that as a hard and fast rule. It changes. There's things that would impact you wanting to go downstream. There's things that might say you could stop short. But as a general rule, it's a pretty good one as a starting point when you're trying to estimate what's going on. The real way to figure out if you're having an impact is to actually do that hydrologic assessment. So in this case, Scott broke out quite a few basins. He was being thorough. He was being detailed. One basin a lot of times is all you need upstream of your site to evaluate the timing of that site. Maybe it's not going to give you all the detailed hydrology that you would do if you were studying this entire stream from top to bottom, but it's going to give you a pretty good idea of what the timing is just downstream of your site of that hydrograph. And then I can develop a hydrograph from my site, and I can see if it's having any impact. If my detention is now putting those in more of a peak-on-peak hydrograph situation, that's probably not a good thing. In this case, we had increased Q coming off of our site, but because it was hitting before the major runoff of the overall watershed, detention wasn't needed, so it wasn't causing an impact. So that was kind of the concept of the downstream assessment. You correct me if I miss anything here, Scott. So, okay. So that's really what it's about. So as far as how far downstream do you go, the 10% rule is a good starting point. Yes, sir.
My comment is, yeah, that's fine, but most communities require you to design your project for the fully built-out watershed condition.
Yes, sir.
So when you do that, you may have to do additional analysis of the watershed that's not yours.
Mm-hmm.
So you can say what's the impact of your site when it's fully developed and the rest of the watershed is fully developed. And you may run into a situation where that's not acceptable downstream because finished floors are too low or something else.
That's
so
a
you
great
have to look
point.
at that.
That's a great point. So I think the point being that the different communities have different requirements, right? And so in some cases, you may have to run the entire watershed as fully developed, and then you would run your site as a pre- and post-development, right? And then you see if your post-development, if you're fully built-out watershed and fully built-out site, if it's causing negative impacts downstream, you would need to mitigate, right? So I think that's a great point. And I think any time that you'll have something like that, a community that's doing it a little bit different or something that needs to be clarified, that's an option that communities could implement. It's a great point.
And then sometimes the city has a lot of that information available.
Mm-hmm.
So you have to ask the city, see what they have. Sometimes the city might have future capital improvement projects that get you there. And then the sticky issue is what's the timing? Who goes first?
Great point. Great point. That actually kind of leads into our other example, which I'm going to go backwards to get to. But you know, we're talking, you know, this one that we just looked at was kind of a greenfield site, right? I mean, it's greenfield being there's nothing there before, and then you develop it, and then you got to figure out what to do with it. Well, a lot of times we have infill areas that we know have issues, right? We know we have issues already, or we know that there's going to be issues in the future if we continue to develop without mitigating any of it. So, Ramin, you recognize this one? Okay. So I had to check first. So, you know, the idea of an adequate outfall is, again, I think a lot of times what that means is you're going to look at either a master drainage plan, you could be looking at a watershed study that someone has, or you could be looking at what Grand Prairie has here, which is, you know, they basically looked at the capacities of all their pipes. In my opinion, that's really developing that adequate outfall for you, or telling you whether you have an adequate outfall or not. So there's no legend here, it got cut off, but the concept being that the green and blue pipes have good capacity in those pipes for either the 100-year or the 10-year event, depending. And the pipes that are red have less capacity. They might have, you know, 2-year, 5-year, something in a lower capacity than what the city requires. And so this is all based on fully built-out conditions. And so if you were to come develop in these areas, you would know that you've got capacity issues on this pipe. I know that that's not an adequate outfall because Grand Prairie has already pulled the plans. They've run the analysis. They know what their runoff coefficient was based on. That pipe was designed and built several years ago, and it doesn't have capacity for the development that's coming there. So you know all that coming in. You know that when you pick up, when someone goes to buy a property, they know that. So what this has done is it's moved forward the identification of the adequate outfall to where somebody should know that immediately. They shouldn't have to do much analysis. So I think that's one route. I'm going to say it's a lessons learned or something that's a useful tool. Has it worked well, Ramin?
Actually, a couple of comments to go along with that. Identified the red areas. Actually, we're doing a current CIP project.
Right.
To go ahead and upsize that storm drain system so to be able to handle that. And a couple of comments or here the approach that we've taken overall, to just make a general comment, is we've looked at an overall drainage master plan for the whole city. And so that way it takes a lot of the burden off of the development to be able to then have to go make that analysis. We have that information available for developers coming in where all we do is plug it in to see what impacts it has on the specific development itself. Just one last comment too, to go along with what was stated before. As far as in general for Iceland, the approach we've taken is that we feel that it's great practices, but we're not going to at the same time, certain things we are going to require, certain things we're going to leave it up to the developers. If they'd like to implement some additional stuff, definitely encourage them to do so, but up to a certain limit in terms of our requirements.
Thank you for that. Anything? Okay. So yeah, so I think this is a good example, I think, of an implementation of a unique approach to identifying that adequate outfall. And like we've said on many occasions, it seems like when you find out bad news, you want to find it out as early in the project as you can. I think that's everybody's situation, and it's inevitable it happens. And so I think this, you have a pretty good picture of what your city looks like as a whole, and hopefully it allows people to plan in ways they can address that. So. Yeah, so that would be an idea of the adequate outfall. Like I said, not everybody has this information. In the absence of this information, if I was going to develop on that site and I wanted to know, I would go pull those plans and see if it was designed to convey the capacity of my site. And if it was, then I can identify an adequate outfall. I can provide those plans. I can show where I haven't changed the drainage area or haven't changed the runoff coefficients, and my Q is less than that pipe was designed for, and I can go on about my business. So some things to consider. So we'll throw out one more. So the first one we looked at was a greenfield site, right? And that comes up quite a bit. And we're looking at more riverine. We're looking at hydrographs. We're looking at larger watersheds. But a lot of our cities are really trying to focus on this infill, this redevelopment, just bringing growth back into the core. And that creates its own set of challenges, its own set of issues. And so I thought we'd be really missing a big part of the conversation if we don't talk really about that infill development and how that occurs. And so in this case, it's a redevelopment area that was a residential area that someone wants to transition into more pervious. They're going to add pervious area in here. And I apologize. Let me explain. So we've got green being the watershed boundaries. The red is our proposed development site that we know we're going to add increased imperviousness to. And then the yellow being the existing storm drain lines. So this is I would say a traditional infill development. And the process for doing a downstream assessment in this case, the effort involved would be to go look at the entire drainage area coming to our outfalls. We have two of them. So this is B, this is A. And my site is split between these two. So I identify my outfalls, right? I know where my water is going. And I evaluate the system from that location all the way downstream until I've established my zone of influence or an adequate outfall. In this case, A was identified as an adequate outfall. We know that the water, if we can get it to point A, it's going to be conveyed, and we got no issue downstream. In B, we actually had to go use the 10% rule and go downstream far enough to where we could consider our site not having a significant impact on the watershed, right? And so we've gone downstream. We know that we're increasing some discharges over here, but we've gone far enough downstream to where we don't think it's going to have a major issue beyond that point. We run and I'm trying to show you this to show you kind of get a feel for the amount of effort. I've got 2 or 3 basins. I run the rational method. I've got my increase, my pre and my post from my site. I've got a storm drain that I can evaluate the capacity for. I don't have design plans, so I can run an HGL and figure out if that additional Q is going to have an impact or not. So the key being that once I identify my zone of influence, I've got to evaluate the hydraulics all the way up. So that means I've got to evaluate the pipe capacity, the street capacity, the curbs, the right-of-way. How is stormwater being conveyed, and is it adequate, or am I causing an increase downstream that could be considered an adverse impact? So this is what we see a lot of too, infill. It's not all just open channels and riverine. A lot of times it's rational method and street sections and pipes. And so I think the 10% rule is a good generalization for both of these applications. I think in the infill, you can also use some judgment to say, I've got a sump inlet just down here, just on the other side of B. 100 feet downstream, I've got a sump inlet. I think you should probably keep going. I mean, that sump inlet's right there. That's going to be a condition that might have negative impacts. I think you might consider going further downstream. Hydraulic structures. If I've got a bridge that's just upstream or downstream of B, I think it might make sense to let's look at that hydraulic structure. Let's look at a major culvert crossing or a roadway crossing. Different people have different rules. I would say there's not there's not a whole lot out there that people are doing much different than what's being done in the iSWM manual. We've looked at a lot of communities. There's no silver bullet out there. I mean, there's nobody that can say this is the hard and fast rule and you use it every time and it works every time. It's not. It takes some judgment calls. It takes some discussions with different folks to get that figured out. San Antonio, just to give you a perspective of what this can mean, I mean, San Antonio right now uses a rule that you go 2,000 feet downstream. And that's a way to give you kind of an expectation when you start of how far downstream you might have to go. So there's a few different ways. There's some judgment that gets involved, but that's generally how we do the downstream assessment. So does anybody have any questions, comments? Have you run into a challenge here where you feel like you couldn't get on the same page with someone in regards to how far downstream or what your impacts were? Does anybody have any scenarios you'd add to this?
Just a couple of comments there. What we have is we have identified areas that have had flooding problems. So where we know where we have flooding issues, we take that into consideration. One of the tools available nowadays is also a 2D analysis, because your usual normal method figures out what your pipe can carry, but it doesn't figure out what goes over it. So with that 2D analysis, it tells you what really is happening out there. It's a little more effort, a little more cost, but it gives you a lot better information that you can work with.
Yeah, well, that's a great point. And the 2D really being thriving in situations where you don't have water just inside of your right-of-way, right? When if you can hold it within a channel or a right-of-way or a pipe, our traditional calculations and methods are appropriate. When that water splits and goes 3 ways around 4 houses, it's really hard to calculate that with a rational method and a cross-section. So it's a great point. Thank you, Remy. All right, on to stream bank protection. I guess this is still me. I'm going to keep going. I was looking to pass the baton there. Y'all saw me. So we'll keep going. These guys are going to chime in and tell me what I do wrong, maybe afterwards. But okay, so let's assume we've done our downstream assessment. We figure out, guess what, we don't have capacity downstream, or we have a stream bank erosion issue downstream. Now what do we do, right? We want to just figure out the answer and say it's okay, we checked it, and just do our, check the box and go on. But, okay, we can't check the box. You've got a highly erosive stream downstream. You're increasing velocities to it, and we know we're going to have an issue. So what are our options? There's 3 options here. You can go through and you can reinforce or stabilize that downstream condition. You can go off of your site and try and stabilize it so it can convey the water that I'm bringing to it or the negative impacts I'm potentially causing on it. Option 2, I can install stormwater controls to maintain the existing downstream conditions. So let's say it's not terrible yet. Let's say it's starting to potentially have some issues. Well, I can address those conditions on my site such that I'm not making it any worse. I can prove that I'm not making it any worse. So if I can do that, then I can meet the requirements of option 2. Option 3 is that I can control the release, and this is of the 1 year, 24-hour storm event. I can contain all that water on my site and release it over a 24-hour period. And that release is such that, again, statistically speaking, by people that have looked at this a whole lot more than I have, that if I can release that water over 24 hours, then the odds are it's not going to contribute significantly to the stream erosion or stream bank erosion downstream. All right? Stream bank erosion is really one of the really big issues, I think, that affects our region. And I think it's going to be probably something that affects us worse and worse as things go. I think that, well, I'm getting a soapbox got pulled out here. I just stood up on it. Okay, sorry, I didn't realize that. But if you look at it, I mean, we've got a lot of tools at our disposal for flooding. So we've got flood maps, we've got risk maps, we have regulations and policies. Erosion risk is much more harder to define. A lot of people I think if you go back to the early 80s or late 70s, it's probably what it felt like to develop and not have any flood information available. Back before we had a lot of models and delineations of flood risk, and you were kind of flying blind. To some extent, in some cases, it feels like that with erosion. If you're the first person into a watershed, I don't feel like you can get far enough away from that creek because you know it's going to move. You just don't know exactly where it's going to move or how it's going to move. So it's very unnerving, I guess, when you get in here. And so just some things to think about. All right, so some lessons learned. So there are people that are looking at this, and there are people that are looking especially at the watersheds that aren't already fully developed. So in the the outstretches of the region where people are have mostly undeveloped creeks that are starting to develop, and they've seen the issues that it's caused in the more urban areas that have been developed for 20 years. You can see how that creek is downcut, how it's widened. And so they're trying to be more progressive in some of these areas and make people look downstream. In situations where they're causing major velocity increases, there are situations where they may have to go downstream. You may have to put in some grade control structures. You may have to try and ensure that stream is not going to downcut as a result of that development. And so, you know, there are people out here that are looking at that are concerned about it, and that are trying to learn from the situations that we're in some cases. Gonna mess anything up? Did I get it? Broad overview. It's a good. A lot more things to drill down on. Yeah, absolutely. You could get much more in depth. We could do an entire 2 hours just on that probably. So, flood mitigation, very similar situation. I've looked downstream, I've got flooding issues. Just like Ramin said, I've got a hot spot, I've got identified downstream. I can't increase discharges here. I don't have an adequate outfall, and I know anything that I do is only going to make that situation worse, and I can't do that. So my options, I can provide the adequate downstream conveyance system. This was the question earlier about who goes first, right? Who builds the pipe? You know, if I'm really wanting to go, the city hasn't built that pipe yet, am I going to go downstream and try and improve that system so that I can develop my site? Option 2, install the stormwater controls to maintain that existing downstream conditions. So this would be the situation where maybe I do something on my site to try and make sure that any increase that I've caused is not going to be negatively impacted, negatively felt by those downstream. And then option 3, in lieu of doing the downstream assessment, in lieu of doing all of that off-site, there is an option to simply maintain that existing runoff condition. So I've done detention. I've put in stormwater controls or low impact development or whatever it is, some combination of all of the above. And I've shown that I'm not increasing the runoff downstream. There still needs to be a conscious look, like we talked about, to make sure that I'm not making anything worse, understanding what hydrograph timing could do. And there still needs to be an idea that could happen. But if you maintain the existing runoff, and if you look at it and provide some conscious judgment about how that's not causing a negative impact, then that is an option that can be considered for option 3. So with that, any questions, comments, thoughts on either of these two, streambank or flooding?
Option 3 is normally easiest for infill development where they already have impervious cover.
That's a good point. Option 3 being easier for infill development, right? And a lot of people will choose this. A lot of people will say, I could go analyze it and figure out it's not going to be an impact, or I'm just going to detain. I'm just going to be done with it. Some people, it's a timing-wise decision where they've got to make a decision right now, and they don't have all the analysis yet. And so they say, I know if I design a detention pond, I'll be good. So let's design it now and build it and not worry about it. So it's a good point. Anybody else?
And those detentions can be an amenity. A lot of them are used as retention, and that adds to the community.
Right, right. Some really good examples of that. So, yeah, a lot of them become the multi-use facilities and things like that, and we'll get into that probably a little bit more here in a second. So, all right, we'll keep on moving. Stormwater conveyance systems.
All right, if your brain's turned to mush yet, too much, ready to keep going? All right, stormwater conveyance systems. So, realize we're getting a little short on time. I'll try to get through this. I want to make sure I get your feedback. So, once again, just want to reiterate a lot of the things I'm going to present here are things from the COG manual. I know different communities have different requirements. Just want to make sure we're all aware of that. Say that one last time. Okay, so just some general considerations for stormwater conveyance systems. We want to try and maintain compatibility and minimize interference with the existing drainage patterns. I know Ben's already kind of hit on, multiple times I think we said, just kind of from the very beginning wanting to get some insight on where water is flowing through your site or around your site. What are you discharging to existing storm drain, to existing channel, to a creek. Just trying to, just considering stormwater from an earlier standpoint when you start to develop a site. It's just critical to maintain compatibility with the existing drainage pattern and existing infrastructure. Control flooding, obviously we want to do that. We want to minimize impact to property structures and roadways. Definitely need to consider environmental impacts with water quality, erosion, and habitat. And this is something I don't know if we've mentioned yet, but when we're designing stormwater conveyance systems, the watershed conditions will be fully developed. So any feature that you design, whether it be a storm drain or an inlet, a detention pond, whatever it may be, those need to be sized accordingly based off a fully developed watershed condition. So any drainage area contributing to that system needs to be considered as fully developed. So I know we mentioned design storms a little bit. I'll hit on it here because I'm going to mention these a couple times. There's obviously the stream bank protection, conveyance, and flood mitigation. Won't hit much on water quality here on my slides. We'll start talking about different storms, the stream bank protection storm or conveyance storm, flood mitigation storm. COG manual would say stream bank is for the 1 year, conveyance would be the 25-year, and the flood mitigation is the 100-year. So I'm going to use these terms throughout these slides. When I say conveyance storm, I'm referring to the 25-year from COG's perspective. Now that does change from community to community, so when you do a site plan or you do put together an iSWM submittal, you need to be aware of what community you're in and what events need to be considered for your analysis. Okay, so streets and stormwater inlets. So we'll talk about depth of flow in the streets. You need to consider the conveyance storm, and for the conveyance storm, which obviously changes from community to community, shall not exceed the top of curb or maximum flow spread limits. And then the flood mitigation storm, the 100-year storm, it shall be contained within the right-of-way or easement. So with flow spread limits in the street, looking at the conveyance storm, and you're going to look at different roadway classifications. So table up here at the very top, table 3.7, you see a distinction between collectors, arterials, and thoroughfares and residential streets, and then the different requirements as far as the depth of flow or the flow spread limit, depending on what roadway classification you're in. Now, this is only broken into two categories here. Different communities will have this broken out maybe in a little bit more detail, maybe a little more detail on dry lane requirements and whatnot. I put these two spreadsheets in here. This is just kind of maybe a rule of thumb you could use. So we've put together these spreadsheets that kind of help us from a reviewer's perspective when we look at residential street capacity and right-of-way capacity. So this is your typical 29-foot roadway section or residential street section. And what we've done is we've input a lot of these values in the Manning's equation, and all we do is we change this slope right here, the longitudinal slope. And so you can see, just kind of a rule of thumb, if you're at 1% longitudinal slope along your roadway, your street capacity from curb to curb should be roughly 40 CFS. And then for the actual right-of-way capacity, should be somewhere in the 75 CFS limit. I did notice, like as you increase 0.5% in your longitudinal slope, for your residential section, you add about maybe 15 CFS or so, depending on how you change that up or down, whatever the slope may be. And then for residential, for the right-of-way capacity, it's actually more like 15 CFS or so. So anyway, just as you go, it's just something to kind of keep in mind. Each change in 0.5% grade roughly equates to about 8 CFS more increase or decrease in residential street capacity, and then maybe 15 CFS or so for residential right-of-way. I think it's just kind of good just to see these numbers at 1% and kind of use that as kind of a baseline. It helps me when I review submittals. And I'd recommend too, if this is something you're putting together, or if you are a reviewer, this would be a really good tool to use, kind of help you quickly check capacities of street sections. Okay, storm drain pipe. For pipe design, you're looking at the conveyance storm from the COG manual, and your HDL needs to be below the throat. For velocity, definitely there's going to be maxes and mins. The maximum is from table 3.8. You can see the values up there depending on which type of storm drain it is, if it's a culvert or a main, a lateral, whatnot. Those values definitely change from community to community. I will say there's the minimum 2.5 feet per second. That's so you can have the pipe is actually self-cleaning. so you don't have much sediment built up in your pipe. Slope-wise, 0.5% is the minimum slope according to the COG manual, or the slope that would produce that minimum velocity of 2.5 feet per second. For manhole spacing, just for for maintenance access, you're gonna need those to be spaced every so often. You don't want like a long 2,000-foot stretch where you have no way to maintain your pipe. So there are requirements on manhole spacing for access. Obviously, that changes based off your pipe size. Okay, so hydraulic design of open channels. The design frequency would be the flood mitigation event or the 100-year event. And I want to really hit on this multiple stage concept when you do a channel design. So you want to have just kind of low flow, high flow events kind of in mind. So I guess the idea being you want to try and mimic what's going on in nature. So if you're going to put in a channel, you want to try and mimic what would go on in nature. So there's going to be kind of your low flow events, maybe your everyday events. You want the channel to be able to have a path for those. And then, obviously, since you're going to be designing the flood mitigation event, so your top of banks are going to want to be able to contain that event with a foot of freeboard. I'll show you just kind of an example here. This is a picture. This originally was a 30-foot wide concrete line channel, and it just had a flat bottom. And so you can see a lot of sediment dropped out. You see a lot of sediment accumulation, and then you got grass growing on there. So now it's there for good, and you can actually see how the stream's actually made itself its own little low-flow channel. So just kind of keeping that in mind when you're designing channels. If you don't try to mimic if you don't try to mimic what nature does, it's to find a way to do it itself, and you're going to end up with a situation like this where you have a bunch of sediment built up in your channel. I won't go too much into the geometry or velocities. Velocity obviously depends on what kind of vegetative type you have for an earth channel. Generally 6 feet per second is the max. I think most of you are aware of that. As far as analysis goes, the COG manual requires a HECRAS or similar capable software for water surface profile computations. Okay, culverts and bridges. I'll go through a few requirements here for culverts. The design frequency there is also that flood mitigation event or the 100-year event, and you're going to want to have at least 12 inches of freeboard, lowest point in your roadway or pavement. Tailwater is a big thing I've seen with culverts needing to know what's going on downstream. Are you in a true free outfall type situation? Are you discharging to an open channel where you may need to have some sort of staged storage curve downstream so you know what kind of tailwater impact you have and what you're tying into? Culverts in series, so if you have multiple culverts, you need to take that upstream headwater from your downstream culvert and make sure that's your tailwater for your upstream culvert that you're designing. And then lake or pond, obviously you need to know if you're going to be tying into a lake or pond, know what that elevation is, what is that max elevation going to be considered for a tailwater condition. One thing I have noticed, when you put in a culvert, obviously you can create kind of a damming effect with the water backing up. That can have a significant impact on properties upstream. I've seen that on a couple of reviews where you can see the water surface increase by 2 feet, 3 feet upstream, and that obviously has a big impact. If it's your own property, maybe that's okay. Maybe you've considered that. Maybe it's your own little open space, and you've designed accordingly. But if it's someone else, if it's your neighbor, obviously they don't want you increasing that much on their property. Let's see. Velocity limitations, there's actually none specified in the COG manual for RCP, but for a CMP, it'd be a max of 15 feet per second. Once again, that minimum 2.5 feet per second is in there to ensure that self-cleaning. Slope limitations, a max 10% for RCP, a max 14% for CMP. I'll jump over to bridges. So a bridge would be defined as any cross-drainage facility of 20 feet or larger, and the freeboard requirement for the bridge would be 2 feet from low chord, according to the COG manual. Okay, detention, everyone's favorite subject, is where we have a lot of concerns. It can be confusing at times, designing a detention pond. It can be an iterative process. I think it's fun. I enjoy doing it. Maybe that's not the case for everybody. But with detention ponds, you can use the modified rational method according to COG manual. Now, I will say there are adjustment factors in the modified rational method when you use the COG manual. So we see that it's very common. Someone will submit a design for a modified rational method calculation for detention pond within it's an iSWM community, but maybe they're not aware of or just didn't see that there's actual adjustment factors that apply when you use the modified rational method. That's really to account for undersizing. What it does is it kind of scales up your rainfall, and you end up with a higher volume requirement, and consequently that affects, you know, your outfall design and whatnot. So I just really want you to be aware of those adjustment factors when you're going to be using the modified rational method. You need to be considering those. Those are in section 1.5.2 of the Hydrology Technical Manual that I think Ben mentioned earlier. There's a good link to that on the COG website. But be aware of that for sure. Obviously, you can use detailed unit hydrograph methods. That's probably always the safest way, the best way to actually route water through a detention pond. Rated outlet structure. So I mentioned earlier the different storm events that you're going to be designing to. So you're going to have to design your outlet structure in such a way that it makes sense for all those events that are being considered. Emergency spillway. So if you're going to have a pond, you've got to have an emergency spillway. I actually have an example here off to the right. I think this is a really smart design in one case. This is actually an infill development. You can see the pond here kind of in the middle, and kind of on the outskirts here is a lot of residential properties. And there's a sump area off to the north up there that under existing conditions is already pretty full. This may look familiar to you. But anyway, I thought it was really smart what they did with this spillway. Instead of actually putting their spillway over here with their outlet structure, they actually put their spillway off here to the backside. And so according to the manual, you're supposed to run an emergency situation with your closed conduit system fully clogged. So then where's that water going to go? Now, if you had your spillway here, then obviously you have a lot of structures to contend with, residential properties, existing properties. But if you put it back here, this water can flow out now and actually come down the street and be conveyed within the right-of-way. So that was a really smart design, really well thought out as far as emergency spillway situation, kind of infill development. Okay, rule of thumb, have a start over there. So this is a rule of thumb for detention volume requirements. So this is more kind of a planning stage. If you're going to go from undeveloped to residential, you're going to need approximately 0.2 acre-feet per acre of storage. When you go from undeveloped to commercial, you're going to need approximately 0.25 acre-feet per acre of storage. So this is really key from the very beginning when you start determining where you're going to put your pond, how big is it going to be, how much developable property do I have. This is a real good rule of thumb to use kind of off the bat. It's kind of a good planning tool. This is Stephen's slide.
I'll sit here and talk. You can
I'll stand there. Sure.
So I just had some other lessons learned. We do detention pond reviews for some of the municipalities that we're doing reviews for. The first one is sometimes engineers like to use Pond Pack or another proprietary model to do their detention pond design. They'll submit their plans and they'll have a note on there that they use Pond Pack, and there's very little information. It's really hard to review those plans. So if you are submitting a project with a Pond Pack or a proprietary model, just remember to include that model with your submittal. So the engineer won't have to ask for it, or the city doesn't have to ask for it down the road. Like Scott said, include all the applicable storm events. Check with the authority that you're working in. If they use something different than what the COG shows for iSWM, make sure you're using those storm events, that you're checking each one of them. A good rule of thumb is to show your final stage storage and discharge tables to confirm that your post-project flows do not exceed the pre-project flow requirements. So it's an easy check for the reviewer to see, number one, is the post-project lower or equal to the pre-project? So, and also to show that same stage discharge elevations if you have a riser box or an outfall detail, show it to scale and show where the 1-year event is and where the 25-year event is and where the 100-year event is. Show it on there. It's another good check for reviewers to make sure that what you're designing is correct. Again, provide emergency spillway. You can kind of see a good example here. A little bit different than what Scott showed, but their emergency spillway is actually right next to their outfall, just to try to find a location where it can drain to if that pond fills up. Let's go to the next slide, Scott.
There you go.
Just a couple more lessons learned. Some authorities require landscape and irrigation plans to go with your detention pond design. Check that. If you have that, include that on your first submittal. That way it can be reviewed and checked to make sure that your detention pond has proper vegetation, landscaping, and irrigation. Sometimes the authority requires a fence to be put around your detention pond to make sure that you understand what type of fence is needed and include that with your plans. Sometimes the pond can be constrained on site because you don't have as much area, so you may need to put in retaining walls. If the walls are over 4 feet high, make sure there's a structural design included for those walls. Also, if you're going to have, if your pond is really going to be bounded by walls, make sure you have good access into the pond for maintenance, so some kind of ramp to get down into the pond. And then provide a maintenance plan on the detention pond plans itself for future maintenance. Those plans, along with the plat, will ride with the property over time, so it's a helpful way for the future owners of that site to understand how they need to maintain your pond over time. And again, look at your downstream conditions, what you're draining into. Are you draining into something that's free-flowing? Is there going to be some kind of HGL downstream that you need to consider to design your pond? So there's just a couple more lessons learned that we have from some of the reviews that we do.
Don't forget the time frame.
The pond frame, yeah, that's the pond maintenance note.
The thing you want to watch on the dry detention ponds in particular is that the thing will actually go dry at the end. Flat bottom detention ponds are basically a stinking mess.
Yeah.
Right. That's what I missed, yeah. Make sure it has a slope and it conveys the stormwater appropriately on the bottom.
If it's vegetated, you're going to have more than 0.5%.
Right.
Yeah. Good point.
And one of the things that we're looking at in terms of how can you, if you're going to have dry detention basins, how can you design those to where they're going to be more aesthetically pleasing and more functional? And when you start looking at a site where you have naturally flat areas or you have the larger swells, say it's been a row crop area and they have large trapezoidal channels that flow pretty well, there's the potential to integrate more landscape design processes and hardscape into that, where you have basically a linear dry detention basin, but it's also an amenity versus your square detention basin on the back of the property.
Okay. Well, I'm going to fly through some of these. I know we got a lot more to cover. Yeah.
I gotta go fast.
Okay. This is just a real quick example of some modified rational method calculations with the adjustment factors. So this that spreadsheet you see off to the right actually has all the adjustment factors incorporated. Looks familiar, doesn't it? Yeah. We thought who was going to be here today. Like, a lot of people are going to recognize these slides up here. So the main point I just want to make with this slide was you need to make sure your Q allowable and your Q out for your outfall structure action balance. So you can see in this table, this is supposed to be, this is the Q you're shooting for, 47 CFS. But you look at your elevation storage discharge table over here, you're actually looking at 35 CFS leaving. So this is not balanced yet. You're going to have to iterate between the actual size of your pond or the actual outlet structure. Those all those things need to balance out and match out. We've already talked about tailwater a little bit. I won't hit on coincident frequency. I did want to mention one thing I've seen a lot of is for detention pond designs that actually tie into existing storm drain systems, and just a failure, I guess, to look at that downstream condition, like what is the HGL that you're tying into? What impact does that have on my pond? Is my pond going to be like backing up water? Is it actually going to be draining during the storm event? This is a real critical thing that I think we need to be aware of, but especially with the detention pond design, when you're tying into existing systems, knowing that downstream HGL and running that analysis. So curb inlets, general rule of thumb, for on-grade inlets, capacity should be roughly 1 CFS per linear foot of opening. For a sump inlet, generally 2 CFS per linear foot of opening. This chart over here, this is at the depth of the right-of-way for a residential street, roughly a foot. And what you're going to get is roughly 2.4 CFS per linear feet for a sump inlet. So this is always just kind of a good check to know this number. For a 10-foot inlet, you should be taking in around 24 CFS or so if your elevation is near the right-of-way capacity. And you can see over here in the design calculations, they have this shows 3.94 CFS per linear feet for a sump inlet, so that's obviously much bigger than this number. So this number is just kind of a good rule of thumb to know for sump inlets, especially when you're kind of doing maybe a self-QC or reviewing another submittal. If my capacity per linear foot is well above this, then there's an issue. And I think what happens generally is up here you have equations for orifice flow, then you have weir flow down here. So you just have to be aware of that transition between weir flow and orifice flow for an inlet, and making sure that you're applying the correct equation when you're calculating your capacity per linear foot. Make sure you're using the weir flow when it's appropriate and the orifice flow equations when they're appropriate. Touch on this real briefly. I hit on it earlier about mimicking nature in your designs. When you have multiple barrel box culverts instead of a bridge, ideally you'd want to include maybe a low flow barrel, so you can convey those kind of everyday events or more of a low flow type condition. This is just one example of where you can see there's a lot of sediment built up on the picture to your left. All those box culverts are at the same elevation. And you can see here, this is after it was cleaned out. It was roughly half full. I just think maybe a low flow barrel could have maybe helped out that situation a little bit there as far as debris and sediment accumulation. Okay, real brief on outfall. This is really kind of more related to going from sheet flow to concentrated flow, concentrated flow to sheet flow, then back to concentrated. So I'll just say on this picture on the left, you have water leaving your site off the boundary in a sheet flow condition, and then you come in, you put in a proposed storm drain. Now you've concentrated it, and now it's just actually going over the bank. So you've concentrated flow, and now it's just going out into nowhere. It's going to be an erosion hazard. It's going to be an erosion concern. This design was corrected here in this case by just extending that outfall to the flow line of the creek. I think the big picture concept there is knowing that if you're going to concentrate flow, you need to be able to take that to the next concentrated flow system, whether that be a pipe or a channel. There just needs to be that thought there, whether it's through a pipe or whether it's through a channel. Somehow you need to get that water from your site to that next concentrated flow location. Okay, turn it over to Stephen. Any questions? Any thoughts on that? Okay.
All right, so we're getting tight on time here, so. All right, easements, flats, and maintenance agreements, section 3.7 of the manual. Just something to think about here are definitely easements. You need easements for your projects. Easements can go on the plat, or they can be filed by separate instrument. You need drainage easements for on-site and off-site improvements. You may need a floodplain easement. FEMA may require, or the city may require you to provide an easement for special flood hazard areas, or they may have a lower flow event that you got to provide for. Temporary drainage easements can be obtained with municipality approval. This could be if you have a multi-phase site and you got your first phase and you need to get the drainage downstream. So you may have a temporary open channel or something to convey that, just in a temporary easement, but that doesn't need to be permanent. when the next phase of development comes in, that temporary easement can go away, so you can finish up your development of your overall site. Also, you want to allow for access, and don't make your easement so small where you can't even get to it or can't even maintain the structures you're trying to maintain. You need easements for detention ponds and any permanent stormwater controls. This could vary by municipality of what is required for those types of easements. And then you can have minimum easement sizes for pipes, different widths, 15 feet to 30 feet wide for pipe sizes that are less than 39 inches all the way up through 102 inches. For outfalls, you may need to extend the length of that easement so you can maintain your outfall structure itself. And then again, you also make sure you have the ability to get to it, to access and maintain it. So you don't want an easement kind of out in space where there's no way to get to it. So think about that as well. There's an example of a detention pond easement that we saw in a recent plat. You can see the detention pond easement is established. Here's the property line up here at the top. The receiving stream is a couple hundred feet away from the property line, yet there's no off-site easement. So something that's going to have to be addressed is how do you take that water that's coming out of the detention pond and get it to the receiving stream. Because that can be coordination with the off-site owner and make sure you can get that permanent easement to convey that water down to the next stream location. A plat should include public and private easements. Any easements to be recorded by a separate instrument. So you may have a certain type of drainage easement that was done previously just by deed. And if you're going to plat that area, you need to include that information on your plat. Include any floodplain easements that are required by the municipality. Provide a legal disclosure on your plat for any drainage provisions. And that's just kind of ride with the property if they're sold or property is transferred to someone else. And then include, like in your plans, the documentation of the maintenance responsibilities that each of these plats have. Any agreements that include the transfer of responsibility upon sale of the property. So here's just a site here, and it has a detention pond easement by this plat. So this is one property. There's actually two other properties to the north that drain into this detention pond. So this property and the other two all have agreements on who maintains this pond, what happens if the pond gets clogged, just so all entities know if you're draining to that pond, how it needs to be maintained, who's going to be responsible for paying for any improvements. All that kind of rides with the property. And again, maintenance agreements and plans. Some municipalities require your maintenance agreement or your pond maintenance agreement to be on the plat itself. Here's just an example. I don't want you to need to read it, but I kind of broke out some parts of this. First, the city of X is not responsible for the design, construction, operation, and maintenance or use of that detention pond. So that lets the owner know when they say, oh, the city needs to come fix this. You know, this may be the owner 20 years down the line. It's not the responsibility of the city to fix that. The owner shall indemnify, defend, and hold harmless the city of X. So that's another thing that needs to be in there. Owners shall require any successor, assigns, or heirs in interest to accept full responsibility and liability for the improvement. So that just shows that the liability and whatever needs to be maintained rides with that property. And again, all the above shall be covenants running with the land. So if you're doing a detention pond in a municipality, you need to understand what maintenance agreement needs to be shown on your plat.
Usually it's obtained drainage easement anyway for emergencies, in case the city needs to step in and clear out something.
Right.
However, we want to be very clear that the maintenance is totally there.
Right.
If you don't include this in the plat, does the reviewer, will they come back and say you need to add this?
Yeah, if that municipality has this requirement, sometimes this is located in the drainage criteria manual, the type of drainage maintenance agreement that particular municipality wants to have. And if it's not shown on there, that's the comment. It's got to be shown on the plat. So drainage reviewers are not only just reviewing drainage plans, but we're looking at the plats too to make sure adequate easements are there, adequate language is also there. That's usually one of the first things we look at. All right, here's just a good example of what happens when you don't provide downstream easements. You can prevent drainage. If you don't have it, it can prevent drainage through adjacent properties without your easement. As you can see here, there's multiple properties This is kind of the upper end of this basin. The water's flowing all the way down through here. It's going through all the backyards of these properties. No easement was included for that drainage. Over time, people build fences, they block the flow. The water's not going where it needs to go anymore. And it becomes an issue that we have to look at and study to find out where the water's going. All this could have been prevented when this property was developed, to include those easements and have adequate drainage through there. So you understand this is the corridor for drainage to flow, you have to maintain it. And it's clearly identified how that's maintained and who's responsible for maintaining that. Any questions on easements? All right, I got 10 minutes. I'm gonna fly through this. All right, now, so we're about to enter the matrix. This is the matrix section of the iSWM criteria manual. This is section 3.8, stormwater control selection. So this is a screening process that you can use to identify what stormwater controls you need for your project. And you can follow along. If you can find section 3.8, you'll see all these tables in here. So again, your design focus area is either going to be water quality protection, stream bank protection, flood mitigation, and conveyance. Again, Scott mentioned the design storms you're looking at. For stream bank protection, 1 year, conveyance 25-year, flood mitigation 100-year. Note, if a development causes no adverse impacts to existing conditions downstream, then it's possible that little or no mitigation can be required. All right, so section 3.8.1, there's 4 criteria for evaluation. You're trying to treat both water quality volume or water quantity control. It could be both, or it could be just one of those. There's 4 different matrices that you would look at. First is stormwater management suitability, then relative water quality performance, if you're looking for water to treat water quality volume, your site applicability, implementation considerations, are those the main 4 criteria. Once you find out what stormwater control you want to use, there's 3 additional criteria that you look at, physiographic factors, soils, and then also special watershed or stream considerations. So again, this is just kind of a screening process. You're trying to figure out what types of control you're going to use, go through these matrices and figure out, it helps you figure out what you need to use for your project. Also, you need to consider any environmental regulations in regards to where structural control is located. You don't want to put your big pipe right in the middle of a wetland, so be aware of those types of things. Each of these tables has different categories of stormwater controls, from bioretention areas to detention, infiltration, ponds, wetlands. So each matrices has those in there, so you can see, do I need bioretention? Is this going to work for my project as you go through those tables? All right, so we'll start with table 3.15. So this is stormwater treatment suitability, and this includes all your categories of your stormwater controls. And then you can look and see if this is a primary control for water quality, for stream bank protection, on-site flood control, or downstream flood control. So I just kind of listed some of the ones that are satisfactory as primary controls for each of these different types of features that you're looking at. So if you're looking at water quality treatment for your project, bioretention can be used, ponds and wetlands can be used, or you may have to use a proprietary system. If you're looking at flood control on site, you may want to do detention, or you can do ponds or stormwater wetlands. And then if you're looking at downstream, same thing. Detention can be used, ponds or stormwater wetlands. All right, so you pick your category, you move on to the next table, table 3.16, the next matrices. This is for water quality performance. So if you're looking to include water quality for your project and you know what type of water quality treatment you need, you can look at this table to see, do I meet the requirements? The first column is the TSS sediment removal rate. So I listed a few things on here that, usually you shoot for 80%. For bioretention, it does provide 80%. TSS or sediment removal rates. It also has information on the amount of nutrient removal rates, bacteria removal rates, and also hotspot applications. Hotspot runoff, those would be areas that could treat, if you have like gas stations or industrial facilities or different types of runoff that needs to be treated through there. So again, this is a screening process, and you're using it to help decide what stormwater control you need. Table 3.17 is the next one, is site applicability. This gives you kind of a broad range of different areas to see what works for your stormwater control. It looks at drainage areas, the space required for your project, for the stormwater control itself, what site slopes work for this type of stormwater control, the minimum head required. You know, if you have a detention pond or a pond, how much head do you need to pass that water through that in a gravity situation? And then also depth to water table. So is there circumstances where you need to provide a certain depth of your control above the stormwater or above the water table itself? And then the last of the four is the implementation considerations. So again, you look at your stormwater controls that you're considering to be used, and it tells you, can this be used for residential subdivision? Is it a good application for that? Is it good to use in a high-density urban area? It also gives you, you know, is this going to be a high capital cost or a low capital cost or kind of something in between? And also, what's your maintenance burden going to be? Are you going to have to spend a lot of money to maintain this over time? So it gives a lot of good information in here as you screen your project. All right, then moving on, you get into your three specific categories. And the first one is the physiographic factors. This tells you some, not for every control, but for some of the controls, some things you need to think about if you're in a low relief area. Say you're in a low relief area and you want to use bioretention. It says to ensure that there's several design variations that will likely be limited by the low head in those flat areas. High relief areas, it talks about those, and those are kind of mainly west of the fourth area. And then also the karst areas, which are kind of limited to portions of Palo Pinto, Erath, Hood, Johnston, and Somervell counties. You can see them right here as this kind of region, far west part of the COG region here. The next table is table 3.2, the soils. And again, here you look at your stormwater control categories, and it gives you some information. If you're going to use detention and you have a type C or D soil, should be adequate to maintain a permanent pool. If you have an A soil or a B soil, you may require a pond liner. So really think about the types of soils that you have in your area, and make sure that whatever stormwater controller you're using for your project considers those types of soils. And then finally, the last one is the specific watershed or stream conditions. So this kind of tells you just a few more things about the stormwater control you have. You may want to place it on a high-quality stream. This is a stream with a watershed impervious cover less than approximately 15%. So you may be one of the first projects to do on that watershed. So you really need to think about what stormwater control you're going to use and how it's going to impact that high-quality stream. Some watersheds, there's a reservoir in it. They may have drinking water protection, and that's just watersheds that deliver surface runoff to a public supply reservoir or impoundment. It may require additional treatment. So one offhand that I can think of is Lake Arlington. In Arlington, they have special requirements for developing your site within that watershed that drains to Lake Arlington. All right, you could have some restrictions. You know, you may be considering where to locate your structural control. You don't want to put it in any location that's prohibited by law. You don't want to locate it in an area that's strongly discouraged. The city that you're working in or the municipality, they may have some concerns about where you're going to place this. You need to check and make sure it's okay to put that there. You may have to justify the location of the stormwater control within that area, and you have to obtain your local, state, and any federal permits first before you can implement the project. Sometimes structural stormwater controls must be set back a fixed distance from a site feature, so consider that as well as you're thinking about your stormwater controls. I got it. There's another checklist in here. It's not a matrices, but it gives you different things to consider if you're going to be where you're putting your stormwater controls. You may have issues with jurisdictional wetlands or stream channels. Those are regulated by the U.S. Army Corps of Engineers. water quality, impaired bodies, and groundwater management areas regulated by the TCEQ. You could have floodplain areas on your project. The local authority may require a stream buffer, like Ben talked about. You can never be too far away from the stream now. There may be utilities that you have to consider, TxDOT roads, local roads, septic drain fields, structural control setbacks, and water wells. There's good information in here about each of those categories that you can read in Table 3.22. All right, I'm going to quickly go through an example, and I think we'll be done. So consider a site in the COG region. It's an undeveloped site, and it's planned to be residential. You have a site slope that's around 10% to 12%. There's a major utility line crossing the site that you have to consider for your development. You did your downstream assessment, you followed Ben's rules, and it does show that detention is required. The municipality does have a stormwater quality criteria, and you do have jurisdictional waters of the U.S. on site. But your downstream receiving stream is stable. So if you go through here's a kind of example site here. And you can see all the existing drainage area. The existing site drains down to this area right here on site. So if you go through the matrices, first you look in Table 3.15, stormwater treatment suitability. Ponds and wetlands are primary control structures for both water quality and flood control, so maybe that's a good option for you. You're thinking about detention, but that's only a secondary control for water quality. It doesn't serve that capacity, and you have to meet that requirement. So you could have a combination of dry detention in ponds or wetlands that the site allows, or you may need just all ponds or wetlands. All right, so you've kind of chosen ponds or wetlands. You're going to go to the next table, your water quality performance. And here you see the ponds and wetlands both have an 80% TSS sediment removal rate. So that meets your criteria. You go to site applicability, the next table, and you see for ponds, the maximum site slope is 15%. That works for your site. For wetlands, the site slope max is 8%. So that may not work for your site. So you decide, I'm just going to use ponds moving forward. You go to Table 3.18, implementation considerations for ponds. Ponds are allowed for residential subdivision use. So that's a good use for it. And then multiple ponds can be used to serve both water quality volume and water quantity control. So you design your site. You have your one pond here, and it's connected to a smaller pond over here. This is where your wetlands are, so you're trying to avoid those areas. Everything drains through those ponds out through here, through the same location where it drained before.
The only thing you've got to be very careful with the ponds, and I think this is brought up in the iSWM technical manual, is you're going to have to have adequate drainage to keep it wet.
Yes. Yeah. You need to ensure that.
That means that water balance, particularly just looking at the scale of your site, would probably be borderline where you would be able to keep it wet. So.
Yeah, you may have to put a water well in, keep it charged. And that pond could be used, again, this could be a dry pond or it could be a wet pond, depending on what the type of amenity that you want.
I'm talking more, I guess, wet ponds. Right. The dry ponds tend to fall into the term of detention, if you will.
All right, so you kind of go to your specific factors here. In Table 3.19, physiographic factors, you're in a low to medium relief area, so it works fine. The upstream pond is 8 feet of normal pool depth. It can be used as amenity and for water quality. The most downstream pond has 4 feet of pool depth. This is mainly for flood control purposes. It can control the discharge out of your site to make sure you're not increasing that downstream. You look at the soils, and you look at the NRCS data. It shows C and D type soils. So pond liner is most likely not required. However, recommended to get a geotechnical report done just to confirm that. You don't need some kind of liner there. There could be some sand seams, or things like that in the area. And then finally, we look at the special watershed considerations, and the downstream receiving stream is not considered a high-quality stream, and no aquifer protection is required. There is jurisdictional waters of the U.S. downstream. It's an intermittent stream. Your ponds only very minimally impact that, so you file your pre-construction notification with the Corps. There was a major utility line crossing in this example. and your ponds are kind of set on each side of that utility line. So you have to work with the authority that you're working with to make sure that you can do your work in that easement, that the connection between those ponds works with the existing utility line. All that's confirmed, you get your plans approved, you use those matrices to design your project, and you get your permits obtained, and then project construction commences. So that's just one example of how to go through each of those tables with a project that you have. All right, and that's all I got. So if there's any questions on how to use the matrices to get into the matrix and out of the matrix, feel free to ask.
That's good. Thank you, Stephen. All right, we're going to skip the last section because I think we're all out of time. So we wanted to prepare enough material so we could cover it. I do think the construction criteria is a really key component of integrated stormwater management. We don't have time to get through it all, but I'll tell you that the construction site runoff is one of the highest pollutants, out there. So we're going to skip all this and go straight to the end that says conclusion. So hopefully y'all don't mind. Hopefully you don't hold that against us. So this was a very technical presentation. I hope that's okay with everybody. We tried to focus on the high points. I will tell you that, going through it and, going back through it again for this presentation, the iSWM manual and the technical manual has an immense amount of information for reference. So just like Lee was saying, if you want to know how much water you need to have in your watershed to maintain a level water pool of a wet pond, it's got that in there. You want to know how much drainage area you should be limiting to a silt fence as a BMP, it's got that in there. It has all this information in there, and it's in a very centralized, great location. I would say we do a lot of reviews of other manuals across the nation. I think there's just an immense amount of information right there that's been developed by the COG and in this region. So hopefully you got a little refresher on that. Hopefully there's a little lessons learned. And again, most of these lessons we learned with many of you, so thank you all for that. And please be very candid in your feedback if you got anything you would like covered, anything that you would like us to do differently, anything that's challenging to you on a day-to-day basis that we need to cover better, please let us know. Derica, do you have anything else to add?
I don't think so.
Okay.
Oh, thank you.
All right. Y'all have a great day. Thanks.